Okay, right now, staggering financial projections for quantum computing are literally colliding with stark warnings from top scientists. We're in the middle of this massive quantum gold rush, but behind the boardroom promises of instant miracle cures and unhackable networks, the actual physicists building these machines, well, they're sounding the alarm. In today's explainer, we're going to look closely at the data to separate the real trillion-dollar potential from the industry hype.
Here's our roadmap. First, we'll cover the trillion-dollar quantum boom, then transforming life sciences, the technical roadblocks, the hype machine, and finally, navigating the quantum future. Let's get into it.
Section 1. The trillion-dollar quantum boom, projecting the financial future.
$1 trillion. That is the staggering projected economic impact of quantum computing by 2035, at least according to the Quantum Insider. And analysts over at ID TechX, they're predicting a massive 30% compound annual growth rate through 2045. So we really aren't just looking at a simple tech upgrade here. Analysts are predicting this is going to become an entirely new macroeconomic pillar, all driven by a level of compute power that our current classical machines just simply cannot touch.
Because of all that potential, blue sky research is suddenly the absolute center of major corporate business plans. I mean, when you have the U.S. federal government injecting a $2.7 billion push through the National Quantum Initiative Reauthorization Act, and tech giants like Amazon, AWS, Google, IBM, Microsoft, and Honeywell matching that energy, things get serious fast. We're talking massive commercial moves too, like IonQ's $2 billion SPAC IPO, and companies like PsiQuantum officially leaving stealth mode. It means we've completely moved from academic curiosity to aggressive commercialization.
And we can actually see exactly how this capital is being deployed to build the infrastructure of tomorrow. Take IBM, for example. They launched their Quantum Heron processor, which is capable of running 5,000 2-qubit gates. That's essentially performing complex logical operations at speeds that literally make classical computers look like abacuses. Then you've got Rigetti pouring $100 million from a direct offering specifically into improving that 2-qubit gate fidelity. Meanwhile, Cisco is already developing the architecture for networked quantum data centers, and QCI is actively delivering thin-film lithium niobate photonic chips to push the hardware forward. The whole landscape is shifting.
Which brings us to Section 2, Transforming Life Sciences, the Promise of Quantum.
So where is all this power actually going? Well, a huge focus is life sciences. The first major step is drug design, specifically simulating complex protein-ligand interactions. Think of it like computationally finding a master key for a very, very specific lock in the human body. Step 2 is quantum chemistry, which allows us to solve the Schrödinger equation to predict molecular properties without ever needing a physical lab. And step 3, biomolecular simulations. That's modeling complex protein folding, which is absolutely crucial for deciphering the underlying mechanisms of devastating diseases like Alzheimer's and cancer.
The difference between the old way and this new way is just night and day. Classical drug discovery is a grueling, slow, incredibly costly trial-and-error process spanning years of physical experiments. But quantum drug discovery? It promises to compress that timeline into a matter of days by rapidly sifting through chemical spaces that are just way too vast for our current supercomputers. When you look at it that way, it's easy to see why big pharmaceutical companies are so eager to partner up with tech giants.
But all of this brings us to the elephant in the room. We see the money. We see the life-saving potential. But is the technology actually ready today?
Let's look at Section 3, the technical roadblocks confronting reality.
To answer that question, we have to understand that qubits, the basic building blocks of quantum computers, are incredibly unstable. Imagine trying to build a massive house of cards in the middle of a hurricane. That is pretty much what it's like trying to maintain a quantum state. In physics, this is called quantum decoherence, the loss of a quantum state's coherence. Any tiny interaction with the outside environment causes them to collapse, leading to errors and noise. And if you're trying to calculate the precise molecular structure of a new cancer drug, you absolutely cannot have random noise undermining the accuracy of your biological computations.
So overcoming these constant errors requires early fault tolerance. Basically, the system needs the ability to correct its own mistakes on the fly. And right now, this is a massive engineering bottleneck. It demands significant breakthroughs before any of those sensitive life science applications can truly scale. We aren't just waiting around for faster processors here. We're waiting for fundamental physics and engineering breakthroughs to stabilize the whole shebang.
Moving to Section 4, the hype machine, ethics in the quantum gold rush. Because of those massive roadblocks, a real ethical tension is building.
renowned quantum researcher Scott Aronson points out something pretty startling about the industry hype. He says, the call is coming from inside the house. Meaning, the wildly overhyped claims aren't just coming from breathless journalists or uninformed outsiders. No, they're actually being pushed by recognized leaders within the field itself.
When millions in funding and equity are on the line, researchers face a really brutal moral dilemma. Aronson goes on to say, it's genuinely gotten harder to draw the line between defensible optimism and exaggerations verging on fraud. It's a tough spot. Professing near-term optimism secures the bag, but it's really starting to blur the lines of scientific integrity.
We are kind of living in two split realities right now. On one side, you have the corporate promise, PR departments pitching that quantum will instantly crack encryption and solve global warming and cancer tomorrow. But then, on the other side, you have the grueling scientific reality. Researchers and labs struggling to just string enough stable qubits together to overcome baseline noise. It's the ultimate expectation versus reality.
Which leads us to our final section, Section 5, Navigating the Quantum Future, Preparing for What's Next.
So, how do we navigate this? Well, smart organizations know they have to prepare right now. They're doing this by forming strategic partnerships between biotech firms and quantum pioneers like IBM and Google. They're also upskilling their workforce for future adoption. But crucially, they're upgrading infrastructure for quantum-resilient encryption and trying to navigate the really tricky regulatory laws surrounding genetic data privacy. And that encryption piece, it is a huge deal. The coming quantum age has given rise to a frankly terrifying strategy by bad actors called harvest now, decrypt later. Hackers are actively stealing encrypted data today, just hoarding it like locked treasure chests, knowing that in a decade, a quantum computer will act as the master key to crack it all wide open. That's exactly why some companies are already deploying global entropy networks to protect sensitive health data in transit. Upgrading our infrastructure isn't some distant 2035 problem, it is a today problem.
I'll leave you with this final provocative thought to consider as the trillion-dollar quantum race continues to unfold. Are we witnessing a world-changing technological revolution, an unprecedented hype bubble, or both? The underlying science absolutely holds the potential to reshape our world, but the road there is paved with immense technical hurdles and billions in speculative hype. Thanks for joining me for this explainer, and remember to keep asking the hard questions about the technology that's shaping our future.